Welcome to my channel. Today we are going to solve one university question from this finite word length effect. So in previous four videos we discussed the quantization noise power problem. Okay, so this is the another question. This is the quantization of filter coefficient problem. Okay, so you see the question for the second order IAR filter system function is h of z is equal to 1 by 1 minus 0.5 z inverse into 1 minus 0.45 z inverse. Study the effect of shift in pole location with a 3-bit coefficient quantization representation in direct form and cascade form. Okay, so here it is a 1 second order IAR system function. So in this, that is what is the question means if you are realizing this second order filter in direct form, as well as if you are realizing this IR filter in cascade form. So what is the effect of shift in pole location? Okay, if this filter coefficients are quantized with 3 bits. Okay, so this is the topic. This is the problem related with the topic quantization of filter coefficients. Okay, so here you see in this filter. So if you are realizing this filter in direct form, what about the shift in pole location? We have to find out. If you are realizing this filter in cascade form, so what about the shift in pole location? We have to discuss. Okay, so first one. So you just note down the h of z. Okay, the given system function, you just write it. Then in the system function, so here there is a z inverse term is available. So if you want to find the pole, you just convert into positive z by taking from this first term, you take z inverse outside. Okay, so if you are taking z inverse outside, okay, so you just take z inverse outside, we can write it as a 1 minus, that is z minus 0.5. Similarly, from this second term, you just take one z inverse outside. So you can write it as a z minus 0.5. Then this z inverse, here one z inverse, z power minus 2. So that z power minus 2, if you give it to the numerator, means the h of z is equal to z squared by z minus 0.5 into z minus 0.45. Okay, so these two functions are equal functions only. Here in terms of z inverse, it is available. Here positive z, the function is available. Okay. Then in this system function, you see, you find out the poles. Okay, so the original poles are, what does it mean by pole? Pole is nothing but a root of the denominator polynomial. So here already is in factorized form. So for the first term, what is the root? 0.5. Okay, so the first pole is 0.5. And for the second term, what is the pole? The pole T2 equal to 0.45. So there are two poles, 0.5 and another one is a 0.45. Okay, so you just calculate. So here we have to solve this problem in two methods. One is direct form, another one is cascade form. So first case, we are assuming it as if we are realizing the second order filter in direct form. Okay, so already the realization of IR filter we studied in that second unit. Okay, so how to realize the given system function in a direct form, in cascade form. Okay, so already we discussed. If you want to learn that videos, means I will give a link for that videos in the description box. You can refer it. Okay, so now we are not all going to realize. Okay, so if you are realizing this filter in direct form, what about the that is a shift in pole location due to the quantization process. Okay, so that is the thing we are going to study. So this is the h of z. So if you are realizing, if you want to realize the given transfer function in direct form, so first the denominator, it should be in the format. Okay, so already we studied, 1 divided by, that is 1 minus a1 z inverse, then minus a2 z power minus 2, etc. Okay, so that transfer function, it should be like that in this format. So that's why you just multiply this two term. Okay, so if you are multiplying this two term, we can get 1 minus 0.95 z inverse plus 0.225 z power minus 2. Okay, so if you want to realize the given system in direct form, so here the denominator, it should be in the form 1 minus A1. This A1 is a filter coefficient. A1 into Z power minus 1 minus A2 into Z power minus 2. Similarly, minus A3 into Z power minus 3, etc. So in order to convert into this format, this two term you just multiply. Okay, so you can get the answer like this. So in this A1 and A2 is a filter coefficient. So here you see 0.95. This is a one filter coefficient. 0.225. This is the another filter coefficient. Okay, so here in a digital filter, this filter coefficients are to be quantized, okay, to 3 bits. So in our problem, there is given the quantization. Okay, so quantization is the filter coefficient. This filter coefficient, it should be quantized to 3 bit. Okay, it is given. So this 0.95, we have to quantize it to 3 bit. Okay, digital data. So for that, so the quantization process we done here. So you see 0.95. Okay, this is the decimal value. So first convert this decimal value, we have to convert into binary. So already you know the method how to convert the decimal into binary. So this is the fraction. Okay, so that's why 0.95 multiplied with 2. Okay, so you can get a 1.9. So the whole number you just keep it. Then again the fraction 0.9 you multiply with 2. So 1.8. Then 1 you keep. Then 0.8 again multiplied with 2 and you can get it. So that whole number we can write it as a. So this is the binary conversion. So finally we got the answer is 0.1111. Okay, so this is the corresponding binary for this fraction number 0.95. Then this digital data, for this digital data only we have to perform the quantization. Okay, so there are two types of quantization already is there, you know, truncation and rounding. So here we have to use the truncation quantization. So truncate to 3 bits. So 3 bits means you just keep the first 3 bit. Okay, then the fourth bit, from fourth bit whatever the value you just discard it. That is mean by the truncation. So after 3 bit truncation you can get the answer 0.111. Okay, then this is the binary. This binary again you convert into decimal. Okay, so you know the procedure in order to convert binary to decimal. So this binary to decimal, that is this one value you multiply with 2 power minus 1. Then this one multiplied with 2 power minus 2. Then this one multiplied with 2 power minus 3. Okay, so you just find the answer and add all these answers. You can get the corresponding decimal value 0.815. Okay, so the 0.95. Okay, the decimal value 0.95 after the 3 bit quantization. The 0.95 it is converted into 0.815. Okay, similarly, the second filter coefficient 0.225. Okay, so for this 0.225 also we have to do the quantization. So that's why the 0.225 first we have to convert into binary. Okay, so 0.225 multiplied with that 2, so 0.450. Then 0.450 multiplied with 2. So you do the process. So you can get the corresponding binary is 0.0011. Okay, so next we have to use the quantization to 3 bits. So you just keep the 3 bit. Okay, so the fourth bit you just discard it. So we can get the answer 0.001. Okay, then this binary you just convert into decimal. So you know 0. Okay, 0 multiplied with 2 power minus 1, it is 0. Then 0 multiplied with 2 power minus 2. Then the third 1 multiplied with 2 power minus 3. So you just add it. So the answer is 0.125. So the filter coefficient 0.225 after truncation, that is after quantization, that decimal value is converted into 0.125. Okay, so that's why the transfer function h of z. So this 0.95 after quantization, it is converted into 0.815. The 0.225 after quantization, it is converted into 0.125. So therefore, the corresponding transfer function can be written as 1 divided by 1 minus, instead of this 0.95. Okay, so instead of this 0.95, you just write 0.875 Z inverse. Okay, plus instead of this 0.225, what is the result? 0.125 you write. Okay, so this is the direct form realization of that thing. Okay, then the second order equation. So if you want to check what about the pole shift, we have to find out. So that's why this second order equation, again you just factorize. So if you are factorizing, you can get 1 divided by 1 minus 0.695 Z inverse into 1 minus 0.179 Z inverse. Okay, so here for this, that is after quantization, if you are factorizing this polynomial, you can get like that. Okay, so that's why the new poles are P1 equal to 0.695 and the second pole is equal to 0.179. Okay, so actually the original pole is, the first pole is 0.5, the second pole is 0.45. Okay, so if you are doing the quantization of filter coefficient, you see the corresponding pole is 0.695, the second pole is 0.179. so there is a major shift from the original location if we are realizing the filter in direct form. Okay, then similarly we have to study the effect of the pole location shift if you are realizing the filter in cascade form. Okay, so you see the cascade form. So if you are realizing the filter in cascade form, so you see, you know, the cascade form is nothing but the total transfer function h of z. It can be splitted as h1 of z into h2 of z. Okay, h2 of z, that each transfer function we have to realize in direct form, and finally we have to connect it in cascade. It is nothing but a cascade form. So that's why you split 1 divided by 1 minus 0.5 z inverse. It is a h1 of z. 1 divided by 1 minus 0.45 z inverse is the h2 of z. Okay, that is in cascade form. So in first transfer function in h1 of z, which one is a filter coefficient? 0.5. Similarly, in h2 of z, which one is a filter coefficient? 0.45. Okay, so in this filter coefficient, we have to perform the quantization process. Okay, so quantization. So quantization means this 0.5, 0.5 decimal value we have to convert into binary. So if you are converting 0.5 into binary, so you can get 0.1000. Okay, so here also 3-bit quantization. So quantization, here we are taking truncation. So you may use rounding also. Okay, so here I am considering truncation quantization. So truncate to 3-bit. So 3-bit means you keep 3-bit, first 3-bit, then from the 4th bit you just discard it. So 0.100. Okay, this is a truncated answer. Then this answer you just convert into decimal. So 0.100. What is the corresponding decimal? The same 0.5. Okay. So if you are quantizing 0.5, you can get the same. After quantization also the same answer we can get. Okay. Similarly, the second filter coefficient 0.45. So 0.45. Similarly, we just convert into binary. So the answer is 0.0111. Okay. Then you just use the quantization to 3 bits. Okay. So the first 3 bit you keep, from the 4th bit you just discard it. So that's why 0.011. Then this binary number you convert into decimal. Okay. So already you know the procedure. 0 multiplied with 2 to the power minus 1. Then 1 multiplied with 2 to the power minus 2. This 1 multiplied with 2 to the power minus 3. You just add it. You can get the answer 0.375. Okay. So here you see the filter coefficient after quantization. The filter coefficient 0.45. It is converted into 0.375. Okay. The first filter coefficient 0.5 is not changed. Okay. As it is the same one. But 0.45 it is converted into 0.375. Okay. So similarly, so therefore after quantization, the transfer function h of z can be written as 1 by 1 minus 0.5 Z inverse. Since in the first filter coefficient, there is no change after quantization. But the second coefficient 0.45 is converted to 0.375. Okay. So here, so for this transfer function, so you see the first pole is 0.5. The second pole is 0.375. Okay. So you just compare this pole with our original pole. So what is the original pole of given transfer function? The first pole is 0.5. The second pole is 0.45. So the first pole is no change. Okay. But the second pole 0.45 is shifted to 0.375. Okay. So that's why, so you see the conclusion in direct form, we can see that the quantized poles, okay, so the quantized poles deviate very much from the original poles. Okay, in direct form realization, you see, so this is our original pole 0.5, 0.45. In direct form realization, the poles are 0.695 and 0.179. Okay, so in direct form realization, the quantized poles deviate very much from the original pole. Okay, but in cascade form realization, we can see that one pole is exactly in the same location, but other pole is very close to the original pole. Okay, so the first pole 0.5 is as it is. The second pole 0.45, it is shifted to 0.375. Okay, so it is shifted, but not that much difference. Okay, when compared to direct form. In direct form, you see the first pole 0.5 is changed to 0.695. The second pole 0.45 is changed, shifted to 0.179. Okay, there is a very much difference. But if you are realizing in the system in cascade form, so one pole is in the same location, but other pole is very close to the original pole. Okay, so that's why usually we are realizing the system. Okay, so in order to avoid the error, the quantization error produced due to this quantization of filter coefficient, usually the filters, the higher order filter, okay, the second and higher order filters are not realized in direct form. Usually it is realized in cascade form. Okay, so that is the advantages of cascade form when compared to the direct form. Okay, so that's why if we want to realize the second order and third order, fourth order system, so instead of direct form realization, we can use the cascade form. Okay, so that is the conclusion from this topic, quantization of filter coefficient. Okay, so finally, so we studied the effect. Okay, so here the question is study the effect of shift in pole location with the 3-bit coefficient representation in direct and cascade form. So if you are realizing the same system in direct form, there is a major shift in pole location. Okay, but we are realizing the system in cascade form, so that the shift in pole location is not that much deviation when compared to direct form. Okay, so we concluded. So this question is one of the Anna University question, December 2011 16 mark question. Okay, so thanks for watching my channel. And please subscribe my channel for more videos. If you want to learn all lecture videos related with this subject, already in our channel in the name of Discrete and Signal Processing, the playlist is there. In that playlist, all videos are available in order. You can use it. Okay, so thank you. We will meet in the next video.